Okay, welcome to this first differential equations lecture on Laplace transforms. This is a repeat of the lecture we had in class. This is a repeat of the lecture we had in class on Thursday, March 30th. So if you were in class and you remember that, this is the same lecture. You could watch it again if you want to review it, but or you can maybe. And by the way, when you watch these videos, you can speed them up, slow them down, pause them, whatever you need to do. I'm going to make a video for each of the Laplace transform lectures. There should be 4 of them in total. And as soon as you're done with them, you'll be free to take an online test. So I'll put that up in the next few days. Okay, so this is Laplace transform lecture number 1. And so this is really the last topic we have in the course. All right, so before we talk about Laplace transforms, let's talk about something called an improper integral. You probably remember these from Calc 2, hopefully. But here's an example. If I took the integral from, say, 1 to infinity of a function like, how about t squared dt. Whenever you have one of your limits being infinity, that's called an improper, because technically if you were to graph this function, whatever the graph looks like, you're trying to find the area underneath the graph to the left of 1 and to the right of infinity. So that area extends forever to the right. If I had a finite number at the top of my integration, that no matter what, that integral would be a finite number. It might be very large, but it would be finite. Now, as soon as you put infinity there, really what this is a limit. This is the limit as a goes to infinity of the integral from 1 to a of t squared dt, where a is, you can think of a as like a slider. Right? Maybe when a is this number here, I'm adding up this area, and then I move a to the right a little bit, and then I add up the area to the total area from 1 to that a. So as a increases, this goes up. As long as the curve is above the axis, it'll go up. I guess it could go down if the curve dips below the axis, because integrals compute something called signed area. Anything underneath the axis counts as negative. But the point is, there's a potential that this may go to infinity. We say that when it does that, it diverges. One way to think of the area diverging is that it blows up. It gets gigantic. Let me give you an example here. Let's finish computing this one. What's the antiderivative of t squared? If you think for a moment, that'll be t cubed over 3. And we're going from 1 to a. We still have this limit here as a goes to infinity. So we're going to work this out. This will be a cubed over 3 minus 1 cubed over 3. Again, as a goes to infinity. Okay, that'll be a cubed over 3 minus a third, again as a goes to infinity. Now think about this. If a is getting very large, and then we're cubing it, it'll get even larger. So this gets large. I'll say it gets larger and larger. It doesn't approach any bound. In other words, it goes to infinity. And then it doesn't matter that you're dividing by 3 and subtracting a third. The whole thing diverges to infinity. That's just another way of saying that the area underneath this curve, if you think of the graph of t squared, it's not surprising. The graph looks like this. We're trying to take the area to the right of 1. You can see visually that as we go further to the right, that area just gets gigantic. Okay, so this improper integral from 1 to infinity of t squared does not exist. It diverges. Okay, so that's always a possibility when you have an improper integral. Let's do another quick example. Suppose I have the integral from 1, how about that? Let's change it to, say, 3 to infinity of the function, let's say 1 over t squared dt. All right, well, this one will be a little different. In fact, if you know what the graph of 1 over t squared looks like, it looks like this. You see how it gets asymptotically close to 0 as you go further to the right. So, and we're starting at 3. We're trying to compute this area here. It does extend infinitely far to the right, but it gets really thin. And because it's really thin, it's possible that the total area might add up to something finite. Well, let's compute it. This is the limit as a goes to infinity. What's the antiderivative of 1 over t squared? Remember, 1 over t squared is t to the negative 2, so that goes to t to the negative 1 over negative 1, which is 1 over negative t. So we got negative 1 over t from 3 to a, which would be the limit as a goes to infinity of negative 1 over a minus a negative 1 over 3. I guess I could change these to plus. Right? 2 minuses make a plus. So we get the limit as a goes to infinity. I'll put the plus at the beginning. 1/3 minus 1 over a. Now let's look at what happens as a goes to infinity here. Well, as a goes to infinity, the 1/3 stays at 1/3. What about 1 over a? You know, think about 1 over a large number. It's like a 1 over 100, and then maybe 1 over 1,000, 1 over 10,000. I think you'll all agree with me. You know, this is 0.01, 0.001, 0.0001, etc. This sequence converges to 0 as a gets large. Okay, so this whole thing will equal 1 over 3 minus 0, which is 1 over 3. So that area, even though it was infinite, kept going infinitely far to the right, still added up to something finite. In fact, it equals 1/3. Okay, so that's just a quick reminder of how to look at improper integrals. You know, there's, you know, a function needs to go to 0 as you go to the right in order for its integral to infinity to even possibly be a finite number. But sometimes even those functions don't add up to something finite. All right, so the reason why we talked about that is because the definition of the Laplace transform, which we'll do next, is in fact an improper integral. Sorry, it should say transform. So Laplace transform. Okay, so here's the definition. So you have to start with a function f of t, a function on t, where t is defined for any number greater than or equal to 0. It could be defined everywhere, but it needs to be defined at least when t is greater than or equal to 0. Then the Laplace transform of f is, this is the way we write it, this cursive L of f of t is equal to the integral from 0 to infinity of e to the negative s times t times f of t dt. That's the definition. It's important to notice a couple things about this. There's 2 letters inside the integral. There's an s, that's not a 5, that's the letter s, and there's a letter t. But keep in mind, we're differentiating with respect to t. So if you were to do this integral, you would end up taking the antiderivative with respect to t, and then you would plug in the limits of integration. Now, one of them is infinity, so you'd have to do that trick where you'd call that a and then take the limit as a goes to infinity. But the point is, all the t's would be gone when you're done with that process. So the result is a function that has s in it. So in other words, the Laplace transform is some function of s. When you take the Laplace transform of a function of t, you get a function of s. In the book, they'll say it's in the S domain. And remember, domain is just a set of inputs, so that just means the input is S. And F had an input of t, so F was in the t domain. Okay, so you can think of a transform as being something like that. It transforms one function into another, and it also changed what the variable is from t to s. Might seem a little strange, but they do have their uses. There's a Fourier transform that's very useful. There's all kinds of transforms. In fact, what makes something a different transform is when they change this function in front of the f of t. This is called a kernel. If you change it to cosines and sines, you can get Fourier transforms. Okay, well, this is the only one we're going to do in this class, this Laplace transform. And if you're wondering why, it's because it'll help us solve some new differential equations that we couldn't solve before. For differential equations. All right, so you'll see that in a couple lectures. All right, so let's compute some Laplace transforms of some key functions. Okay, so let's start simple. A really simple function is the function f of t is equal to 1 everywhere. In fact, we use, when we describe a function as being equal to a constant, we like to put that third line there because it just tells us it's equal to 1 for all values of t. In other words, the graph of this function will be a horizontal line through 1, right? So we want to know, what is the Laplace transform of this function? Okay, well, it'll equal the Laplace transform of 1, which is the integral from 0 to infinity. So this is the solution. The integral from 0 to infinity of e to the negative st times our function, which is 1 dt. This one will be pretty easy because that function that we're multiplying by is just 1. In other words, we're just taking the integral of e to the negative st dt. Remember, when you take the integral of, so it might, having that s in there might bother you, but you could treat s like a constant while you're doing the integration with respect to t. If you take a class in multivariable calculus, you'll learn that when you're doing calculus on one variable, you treat the other variables as constants. So treat it as a constant, meaning you would handle this integration the same way you would handle if it were the integral of e to the negative 10t or e to the negative 6t or something like that. And we're going from 0 to infinity. So the antiderivative, remember the antiderivative of e to the kt is e to the kt over k, right? That's just a rule. So this equals e to the negative st over negative s. And remember, we're going from 0 to infinity, which means we're actually taking the limit as a goes to infinity of e to the negative st over negative s from 0 to a. Okay, that shouldn't be too bad. We take the limit as a goes to infinity of, we plug in a and we plug in 0 and subtract. So e to the negative s times a over negative s minus e to the 0 over negative s. Remember, those are all s's, they're not 5s. Okay, so now let's talk about this. As a goes to infinity, this gets large. Okay, so we have e to negative something very large. That's the same as 1 over e to something very large. Well, e to a large power is just a large power. It's 1 over something very large, which means it goes to 0. So this will equal 0 minus e to the 0 over negative s. Of course, e to the 0 is just equal to 1. The two negatives cancel, and we're left with 1 over s. So this Laplace transform of 1, that's what we started with. The Laplace transform of the function 1 is just 1 over s. It's the new function 1 over s. There's one more thing we have to mention. We have to mention the domain of the new function. Now, that rule that we talked about, how when a gets large, e to the negative sa goes to 0, that's only true when s is positive. Because if s were negative, that whole thing would actually diverge. So this function is only, this Laplace transform only exists when s is greater than 0. Okay, so let's make a table. If we make a table here, f of t, and the Laplace transform of f of t, the first thing in our table will be 1 and 1 over s. where s is greater than 0. So let's keep going. Let's try some other functions. Find Laplace transforms of some more functions. By the way, this table, we're going to fill out a lot of this table today in this lecture. This table will actually be given to you on the exam, including the final exam for this class. The online exam for the Laplace transform, that'll be open note, but even the final exam will have this table. So you don't have to repeat anything we're doing today. I just want you to see it. Okay, it's possible we could ask you to compute one Laplace transform on the test for a fairly easy case where we'll tell you can't use the table to do that one. You have to show your work, but it would be something fairly simple like this. Let's do another example and change colors. What's another simple function? How about f of t is equal to t? That's a pretty simple function, right? Here's the graph of that. It just looks like that. Let's find the Laplace transform of that function. Okay, well, the Laplace transform of t is just going to be the integral by the definition. It's the same steps we did before. It's the integral from 0 to infinity, e to the negative st times t dt. That's the only difference this time. We're plugging in a t. This is our f, or our f of t, our function. All right, so if you're thinking about this integral, you've seen it before, you'll know this is the integral of t e to the negative st. We'll worry about the limits of integration later, dt. And if you're familiar with this, remember we treat s like a constant. So we're doing the same integral as t e to the kt dt. And you might remember, in order to do this integral, you need integration by parts. Okay, so let's do that one. I don't think I'd give you an integration by parts one on the test, but let's do this one so we can fill out our table. This will be the next one in the table. All right, so to do this integral, I think here's the trick. I'll do this quickly. You can pause it or slow it down if you want to see the details a little slower. But you always let u equal t in the situation, and then dv is the rest, e to the negative st dt. And then we compute du. Of course, du would just be dt, and we compute v by integrating this to get v is equal to e to the negative st over negative s. And then the formula is that this is equal to, right, the integral of u dv is equal to u times v minus the integral of v du. Just remember that because I've done integration by parts 1,000 times. So okay, u times v, that's t, because there's u, that's t. You want to express everything back to t's and t's and dt's. Okay, so that's u, which is t, v, which is this here, so e to the negative st over negative s, minus the integral of v du. Well, v is that, so the integral of e to the negative st over negative s, and then du, which is dt, so dt. I still have an integral. If you do integration by parts, you still have one integral left, but this integral is easier than the original because it doesn't have that t in there anymore. That's why it works. So we're almost done. We do this integral, so we get t e to the negative st over negative s minus e to the negative st over another negative s. So a negative s, and we still had the original negative s that was already there. And technically it's plus c, but we don't need the plus c because we have limits of integration. Let's clean this up a little. These two negative s's multiply to equal s squared. So we get negative t e to the negative st over, over s. That's right, I put the negative in front there. And then minus e to the negative st over s squared. And that whole thing goes from 0 to a, and then we have to do the limit as a goes to infinity. Okay, so a lot going on here, but we're almost done, right? So we plug in a. Remember, you're plugging in for t, so a lot of times I like to write from t equals 0 to t equals a because it reminds us which variable we're using. The s is just going to stay in the answer, so we're going to get negative a e to the negative s a over s minus e to the negative a t. Sorry, that should have been, s, I'm getting confused, sorry. That should say negative sa I'm replacing t with a over s squared. So that whole expression minus, now I plug in 0 for t. If I plug in 0 for t right there, I just get a 0 for that whole first term, and then minus e to the 0 over s squared. Now once again, we have to let a go to infinity. Okay, well, as a goes to infinity, you'll notice this first term is a little weird because you have a, which goes to infinity, times e to the minus sa, which goes to 0. Anytime you multiply something that goes infinity times something that goes to 0, it's like you're trying to multiply infinity times 0, and that's called indeterminate because you don't know what the limit does in general. One nice rule of thumb you might remember from calculus is that when you have a polynomial like this competing with an exponential like this, the exponential always wins. That's because it grows and shrinks faster than other functions, especially polynomials. So even if it was a to the 100th power, which will grow very fast, it would still not grow as fast as e to the negative a gets small. So even then, e to the negative a wins. Why am I saying that? What do I mean by it wins? I mean the fact that that goes to 0 will overcome the fact that a is going to infinity. So the whole thing goes to 0. So this whole term goes to 0. Of course, this one also goes to 0 because there's nothing even competing with it. We already know e to the negative sa goes to 0 as a goes to infinity. That's just the same argument we made earlier. By the way, the function e to the negative x looks like this. You can see as x goes to infinity, e to the negative x goes to 0. You can just see that asymptotically. That's why this function here goes to 0. The s squared in the denominator doesn't matter. It's 0 over s squared is 0. So the only thing we have left here is we distribute this negative, and we end up with e to the 0 over s squared, which is 1 over s squared. And again, it's true when s is greater than 0, just like before. All right, so it got kind of messy there. It was a little ugly, but this is the final result. This is the Laplace transform of the function t. Right here. That went to 1 over s squared. So we'll put that in our table. I'm going to scroll here. It's not bad on your eyes. We just did the Laplace transform of t, and we got 1 over s squared for s greater than 0. All right, so it turns out, I don't know, there's a lot of different functions we could try next. Why don't we try t squared? I'll scroll over here. I won't show you all the details for t squared because it's very similar to the last one. So f of t equals t squared. You would get, the Laplace transform of t squared would be the integral from 0 to infinity of e to the negative st times t squared dt. It turns out you'd have to do integration by parts, just like we did, twice. You probably don't want to watch me do that. Okay. If you did take the time to watch me do it, or if you want to try it on your own, it would converge to 2 over s to the third. Okay, so in other words, the Laplace transform of the function t squared is 2 over s to the third. Again, when s is greater than 0. There is a pattern here, actually. Just like there's a power rule in regular integration and differentiation, you can work on you can talk about a power rule for Laplace transforms. So in other words, if I were to try t to the third, we would get 6 over s to the fourth. In fact, here's the formula. If you were to do t to the n power, it'll always work out to n factorial divided by s to the n plus 1. And again, where s has to be greater than 0. And by the way, if you don't know what n factorial means n times n minus 1 times n minus 2, etc., all the way down to 1. So for example, 5 factorial equals 5 times 4 times 3 times 2 times 1, which is, 20 times 3 is 60 times 2 is 120. Okay, so that's how a factorial works. It's that exclamation button on your calculator. Okay, so this is good. Now you'll never, for the rest of your life, or certainly for the rest of this course, you'll never have to compute the Laplace transform of any power of t, because you've got this formula here. All right, before we go on to a few other types of functions, now would be a good time to show you a few nice properties of the Laplace transform, which will enable us to find Laplace transforms of combinations of these functions. Okay, so let me scroll to the side here, make some room. So we're going to talk about properties of the Laplace transform. Well, actually, this will be you should already know these, actually. So since the Laplace transform is an integral, right? We defined it as an integral, right? It's the integral from 0 to infinity of e to the minus st of some function of t dt. Then the same properties that we're familiar with for integrals also apply to Laplace transform. I'll just say the same properties apply. Right? You should already know these. We know that if you take the integral of k times something, times anything, dt, that's just k times the integral of that same thing, dt. In other words, we can pull constants through. If they're multiplied by something else. Okay. Also, if you have the integral of one thing plus another thing dt, that's the same as the integral of those two things separately. In other words, we can split up integrals across addition and subtraction. You're all familiar with this from calculus. So those same two properties where you can pull a constant out and you can split up across plus or minus, those two rules apply to Laplace transforms as well. What do I mean by this? Here's what I mean. I mean that if I ask you to take the Laplace transform of sine of 7t plus t to the fifth, that's the same as taking the Laplace transform of sine of 7t, which we haven't done yet, plus the Laplace transform of t to the fifth. You wouldn't have to do the whole integral again for the function sine of 7t plus t to the fifth. You could just look up the Laplace transform of sine of 7t and the Laplace transform of t to the fifth and add them together. In fact, we already know the Laplace transform of t to the fifth. That's from our table, right? Here n is 5. So this would equal 5 factorial divided by s. Remember, the formula was n plus 1, so it'll be s to the sixth, and that's only valid when s is greater than 0. This other one we haven't done yet. We will in a few minutes. Okay, but so we get our answer and we would just add them together. Okay, so and the other property, remember that was just this one where you can split things up. Remember the other property says we can also pull constants out. So to show you the use of that, suppose I ask for the Laplace transform of 17t to the third. Well, that's the same as 17 times the Laplace transform of t to the third. And we already know the Laplace transform of t to the third, it would be 3 factorial over s to the fourth. Okay, so that would be your answer. I guess 3 factorial is 3 times 2 times 1, so that's 6. I guess we should multiply 6 times 17. I should have used smaller numbers, but it's 42, so 6 plus 4, that'd be 102. So the final answer would be 102 divided by s to the fourth, and this is when s is greater than 0. Okay, so because we knew the Laplace transform of t to the third by itself, we're able to now compute the Laplace transform of anything times it. It's very powerful. So, in fact, yeah, let me do another example here. I'll move over to the right here. Example. Here's a function, a typical polynomial. 6t to the fourth plus 7t t squared minus 1/2 t plus 8. It is a polynomial. If I want to know the Laplace transform of f, I don't have to put this entire function into my integral and redo it. I can simply use those properties to say this is immediately, remember this is the Laplace transform of this whole thing. 6t to the fourth plus 7t squared minus 1/2 t plus 8. And by our properties, that's 6 times the Laplace transform of t to the fourth plus 7 times the Laplace transform of t squared minus 1/2 times the Laplace transform of t, plus 8 times the Laplace transform of 1. We've already done all of these, right? But we know the Laplace transform of 1, that was the first one we did, is 1 over s. That's when s is greater than 0. We know the Laplace transform of t is 1 over s squared. Again, when s is greater than 0. Maybe we'll just, all of them are going to be s greater than 0, so we'll just write that once. This t squared, I told you that's the one that equals 2 over s cubed. And then t to the fourth, that's when n is 4, so this would be 4 factorial over t to the, or sorry, not t, s to the fifth. So we multiply this one by 6, this one by 7, this one by 1/2, and this one by 8. It looks like our final answer, by the way, 4 factorial is 24. So 24 times 6. 144. So we get 144 over s to the fifth plus 7 times 2, so 14 over s to the third, minus 1/2, I'm going to say 1 over 2s squared. I just multiplied negative 1/2 times 1 over s squared, plus 8 over s. And that's all for s greater than 0. That's it. That's the Laplace transform of f in this case. We saved a lot of work by using those two properties of splitting it up across addition and pulling constants out. All right, so all right, let's do our first function that's not a polynomial. We'll add this to our table. So here's a function. How about e to the 7t? It's a perfectly valid function of t. And let's compute the Laplace transform. So this will be the Laplace transform of e to the 7t. It's going to produce a function of s. And let's just go back to the definition. Remember the definition. By the way, the definition will also be on that table you get for the final. It's the integral from 0 to infinity of e to the negative st. It's an s times f of t. Well, in this case, f of t is e to the 7t dt. All right, if I want to do this integral, I want to combine those two exponentials. Remember how it works? If you ever have a to the x times a to the y, that's a to the x plus y. Just a property of exponents. They have the same base. Well, these have the same base, so this is going to be the integral of e to the negative st plus 7t dt. We'll worry about the limits a little later. In fact, if I pull a t out of this expression and rewrite it, I'll get e to the 7 minus s in parentheses times t. That's the same thing as what we had here. I just factored a t out and wrote the 7 and the s in different orders. Okay, dt. All right, what's the antiderivative of that? Well, this is another one. The integral of e to the kt is e to the kt over k. So it's the same thing, just our k is 7 minus s. So we get e to the 7 minus s in parentheses times t divided by 7 minus s. Looks weird, that's an s, not a 5. And technically it would be plus c, but we don't have the plus c because we have limits of integration. This is from 0 to a, and then a gets large, right? A goes to infinity. Okay, so we plug in a, we plug in 0 and subtract. So remember, it's the limit as a goes to infinity. If I plug in a here, I get e to the, I'm plugging it in for t, e to the 7 minus s times a divided by 7 minus s minus e to the 0 over 7 minus s. Okay, So again, what happens here? So as a goes to infinity, as a gets large, when does this expression here converge? It only converges to 0 when 7 minus s is negative. So e to the 7 minus s times a goes to 0 when 7 minus s is negative. Because if it's not negative, then the whole thing actually blows up and diverges. You need a negative exponent for that to go to 0. So 7 minus s negative means 7 minus s is less than 0, which means that if I add s to both sides, I get 7 is less than s, or s is greater than 7 is another way to write that. And when that happens, this equals 0. So the whole thing equals, we still have that negative here, negative 1 over 7 minus s when s is greater than 7. That's the final answer, although there's a nicer way to write it. We could bring this negative sign into the denominator to get 1 over s minus 7 without the extra negative when s is greater than 7. That's the best looking result. That's the Laplace transform of e to the 7t. It's kind of interesting. It's sort of like the Laplace transform of 1, but it's shifted by 7. Shifted. By the way, you could think of 1 as e to the 0t, so it shouldn't be too surprising. All right, well, in any case, let's add that to our table. So let me zoom out here slowly so it doesn't hurt your eyes. Scroll back to our table. Here it is. All right, we're going to have to make the table longer at some point, but by the way, there was nothing special about 7. I just chose it. Let's change it e to the at. Its Laplace transform will be 1 over s minus a instead of s minus 7. And it's true for s greater than a. So if a is 7, you would just replace it, you would just replace all the a's with 7, you'd get what we just did. But if you're trying to find the Laplace transform of e to the 5t or e to the 11t, it would be 1 over s minus 11, and it's true when s is greater than 11. Okay, so how about this? Let's I'm going to start showing you in the next lecture how we're going to use these. So, and this might be a little boring just seeing me do Laplace transform. Let's just do 2 more. In fact, I won't even show you all the details because these are also ones that require integration by parts again. So we'll skip these. We'll do these a little bit quicker than that. So I want to do sine and cosine. So how about this? Let's if we had f of t is equal to sine of a times t. Think of a as just some constant. Okay, then if we started to do the Laplace transform of this, we'll end up with the integral from 0 to infinity of e to the minus st times sine of at dt. A is just some constant. We're going to, in certain problems you might get a is 2/3 or a is 11, but you want the table to be generic so you can plug it in later. You don't want to have every possible value of a in their table. Your table would be too long. So in order to do this antiderivative, you have to do integration by parts twice. So I won't show you all the details. In fact, not only do you have to do it twice, when you do it twice, you get back to where you started, and then you have to sort of create an algebraic equation for this result, and it's kind of a trick you might remember from Calc 2. But if you do all that work, you get the Laplace transform of f. After doing all that work and the limit as a goes to infinity, you'll end up with b over s squared plus b squared. So we'll add that to our table. We'll add that in a second, but before we add it, let's do another one. Let me change colors here. The other one, as you could expect, would be what about f of t equals cosine of t? It's the same technique. The same technique to compute the antiderivative of e to the negative st times cosine of at. Sorry, let's make that at in case you want to have a frequency in front of it, not just t. dt. It's the same technique, but you end up with something else. Again, same method. You end up with a Laplace transform of cosine of at is equal to s over s squared plus a squared. I'm sorry, why did I write b up here? The sheet I'm looking at had b in it, but this was a. I apologize. This was a. A is the frequency in the sine function. Right? So for example, if I ask you for the Laplace transform of sine of 2/3 t, you would get, using this formula for sine, you would get 2/3 over s squared plus 2/3 squared, which would be 2/3 over s squared plus 4/9. You can't simplify anything there because of the plus. So I meant to write a there. I apologize. So for the sine function, it's a over s squared plus a squared. And for the cosine function, it's s over s squared plus a squared. So in other words, if I ask you for the Laplace transform of cosine of 9t, you would get s over s squared plus 81, because 9 squared is 81. And by the way, I should mention when these are true, these are also true for s greater than 0. Okay, so all right, so we handled Laplace transforms of a lot of different functions. You should be prepared to at least do one, maybe on a test, a simple one, not one that has integration by parts. Something like e to the 5t or e to the 8t or just one, or a constant or something like that. So we'll start the next lecture with a quick summary. We'll redraw that table fresh so you can see it again. And all right, see you in the next lecture. Thank you.